So, we start with session 2 of the course. I titled this as ignorance of A is the sin of B, okay, A not equal to B, right. So, you make application software like a compiler, or you make see in normal life, right, your sin, you are going to take the effect of your sin, but in information security, in the computing infrastructure, if you generate a stupid software, a stupid operating system with lot of vulnerability, you are not the guy who is suffering, there will be somebody else who will suffer, okay. So, if you are ignorant about security and you make systems, and for some reason that system becomes popular, as you see many systems today, then the sin that you are committing will be actually, the ignorance that you have will be realized like a sin for somebody else, and they will start reaping the bad effects of that, right. And I am going to give you some case studies here where some stupid decisions in the past, and stupid, I am using that word voluntarily, stupid software that has come out in the market has now made life miserable for somebody else, for which we are not responsible and we are paying to get those software. So, let us go and look at this. See, this is the ignorance of the developer, which is the sin of the user. So, this was something happened in 2007, and I do not see something happening in the same way on recent times. Maybe it was I missed it, but this itself is very scary, and I am sure more recent surveys would be much more scarier, if you could call that word, right. So, 100 commercially off the shelf open source applications were picked up randomly, and they were analyzed, and the analysis is put down as those 6 points. There were packages with dead code, 79 packages with dead code. Dead code is a code which you do not execute normally, but the dead code can be a potential atom bomb, because that can come into existence in some contingent situation where it can go and kill, or it can go and be a major vulnerability, right. Then there were unwanted codes which can be interpreted as backdoors, and there were 23 packages. There were packages with suspicious behavior, around 89 packages, 89% of your software had suspicious behaviors. There were malicious code, known malicious code in 76 packages, known worms, Trojans, rootkits in 21 packages, and possible worms, Trojans and rootkits in around 69 packages. So 90% of your software were not trustable, and this is from some randomly picked 100 commercially off the shelf / open source applications, and this is where you are now heading, and all the software you are executing and all the development environments you are having are taken from this set, okay. So, this is the fate of the user with respect to security, right, and there you are now going to expose your heart, your kidney, your blood pressure, everything on systems running with this type of software, and that is the scare, right. And I think this is the best open problem for any researcher to handle, right, and that is why we say this course is very important. Now, this is a very interesting case study that we get from the web. There was a popular database, there were 3 releases post 2001, and after 7 years somebody casually went through the code and they found certain words like politically, and they went and started analyzing this code. They found that if you enter the name as username as politically and you give the password as correct, you get super user permission into the database. You mean people who have worked in database would understand what it means to have a super user permission. You can entirely go and kill. Suppose your bank in which you are put your money uses this database, some politically correct guy can actually come and completely transfer the money from your account to his account, he can also make loans in your name and transfer that money also there. So it's not just you lose your money that you become accountable for money which you didn't possess or you didn't take. Okay, so the amount of chaos that could happen if something like this existed in the database. Today you are using some N databases for different applications at different sectors, right? Financial sector, strategic sectors, so many things are there, and lot of things used commercially off the shelf. Are you sure that such a thing doesn't exist there? Okay, so every day morning pray God that your money should be safe. Okay, you understand what I mean, right? So this is very, very important, and this is something a disgruntled user would have put something there, and disgruntled developer, and when he is chucked out of the company, he can come out and create ravage about that company. And he would also conceal, may say, if such type of logins, don't even log, put it in the log. If I do this type of access, don't even log these accesses. You can write that. And if you are looking at a typical database code of several millions of lines, this 10 or 20 lines or 50 lines that you need to do this, and that you compile it, right? It can go as a stealth. Nobody can even see this, right? So this is the state of affairs. Now why is this ignorance? I have already explained in the previous thing, but I am going to go depth. The ignorance was that there were several layers. There is an operating system layer, architecture, microarchitecture, compiler, application software, and I said all these layers were isolated. And this isolation was one of the reasons for this ignorance. Now, I can go much more deeper into this, and now we say that today what has happened is functionality has actually moved into hardware. So day before yesterday's software becomes yesterday's coprocessor and becomes today's hardware. A typical example today is the graphics. In olden days, the CPU was doing the graphics, and that's why when I want to draw a line, it goes like this, right? Then this was shifted into it was basically a software. Then what did they do? They got a graphics coprocessor which was doing this functionality. So if I want to do graphics as a CPU, I'll tell the coprocessor, hey, do it. And today what happens, that graphics coprocessor actually has become part of your chip. That's why you call it as a system on chip, right? So yesterday's hardware, day before yesterday's software becomes yesterday's coprocessor, and it has become today's hardware. Now, when I had that as a software, I knew what it was trying to do. Today it has become hardware, it is not even a code. There is no way by which I can go and find out what it is trying to do, correct? So if there is going to be a Trojan or a malware inside that hardware, right, there is no way by which I could go and find it out today. So functionality that ensured security actually moved from software to hardware. We will see some of them as we proceed here. And then there are a lot of vendor specified access rules and digital right management protocols, and we really don't know what it means. Today somewhere you get on the screen, no, there is some problem with the software, should I go and report it? You say yes, report, right? Is it going to report just what you have done, what has happened with the software, or it is also going to take some very confidential information, one directly it can zip and also send it? Are you going to monitor it, right? There is some problem, should I report? You go and click that report key. Is it just sending that report, or it is also sending some other confidential information along with it? You don't know. It can send you a shadow file of your password, right? It can. What is the guarantee it is not doing it? You don't have a guarantee, correct, right? So lot of times you say, no, save the password. You are saving the password in your system so that every time you go and say www.somemail.com, and then you actually get logged in. So this password is stored in some place within your system. In which form is it stored? Maybe stored with something, but is there a guarantee that somebody is not going to take away that password, because your system is always there on the internet? So there are certain access rules, and certain vendor specifies these access rules, and he makes an assumption, because the vendor also works in one of those layers. He is probably working in that operating system layer or the application software development layer. He does not know what the hardware is. There is some level of ignorance about the hardware and the execution environment. So he assumes certain environments and say, in this environment, your confidential information is really going to be stored confidentially. But when it goes to some other environment where some of his assumptions get violated, he is in no position to assure you that confidentiality. Are you able to understand what I am saying? So there are certain vendor specified access rules, but when they are imposed into some other scenario, they make certain assumptions about hardware, and those hardware things are violated, you basically start leaking information. And so there is lot more effort needed to understand security, right? So so this is where we start. Now why is this has become an issue? We are in a shameless age. There are people selling software and they say you need to buy third party products to ensure security. I buy some operating system, along with the operating system order I have to send one antivirus order also, correct? Right? And this is a shameless age, right? So security was not ever in my agenda when I was developing a software. Security was never by default. People thought that security is a major addition to system modules, and it was actually sold at premium price, right? If I want to have, so basically if I need a secure system, so that's going to be much costlier than an unsecure system. People didn't think that security is an inherent blood of your body. They said it's some extraneous thing which you need to add if you want to make your body glow a bit much better, right? And development systems, so when I start developing a software, I don't give a secure environment there. So you start developing the software in whatever in a non-secure environment. You have the basic things to develop a software. So obviously you are not even, so when you compile the software, it is not a secure compilation, it's an ordinary compilation. Because a secure compiler costs much more than an ordinary compiler. So you start compiling it, and when you go to a customer site, there every security is there. You put a software that is developed in a non-secure environment, that has been compiled in a non-secure environment, you go and put it in a secure environment. It never uses those security features. Those are all some, in Tamil Nadu we have this Navaratri dolls, right? Just keep it in the thing and then keep it and do some harati, right? So they are never used, right? They are just dolls. Right? So because you have developed everything in a non-secure environment, your compilation has been insecure. Now you go and put it in a secure environment, nothing comes. So all those security features are just mute watches. So, so the point is, deployment scenarios had the secure features, but the ignorant software which was developed in a non-secure environment could not use it to its maximum potential. This is because when you develop a software, you don't want to give an environment which is costly, which has the security features, so that every time I compile, I subject it to a secure compilation, I subject it to a secure execution. That doesn't happen here, and this was one major mistake. So this is not what I am talking of. Please go and read the paper that you see at the end of this slide. Paul Karger, unfortunately he is not alive, but he wrote a very, very interesting paper, 30 years later, lessons from the Multics security evaluation. So the output, the takeaway from this paper is that the security that existed 30 years before in Multics is not seen in modern day operating systems, and that was the takeaway from this paper. Now I will go and talk about this paper in some detail during this course. Let us talk about this. I will just briefly tell about that paper. That paper is a very, very beautifully written 10-page paper. I suggest all of you can go and search the Google and you can get it. Google it, you will get it. But I will talk about some important points in that paper. Multics was one of the, we could call it as the father of all operating systems. It was a very widely used operating system in 1965 or something. None of us were born, at least I was not born, my previous birth. And Unix and its derivatives uses concepts from Multics. That's why we say it's the father of many operating systems. In 1974, probably many of you would not have born, and I was studying second standard, right? At that point, the US Air Force wanted to do a vulnerability analysis on this software environments. Especially many of them were running Multics. Please note that there was no internet there. There was a minimalistic communication between devices, right. At that point of time, they even thought that there is a need for a vulnerability analysis. This is a very, very big vision, I should say. Even that time, where even tens of or maybe hundreds of computers are connected together, it's not that internet, that the moment I add my cell phone, switch on my cell phone, I am in an internet with 1 billion users or whatever. So, you are talking of such type of things. But even that time, they did a study and they found it was not so promising. The Multics of 1974 today was more secure than the current days. Even that day they said it was not so promising, but what you see now, the Multics of 1974 was much more secure than the current day operating system. And this is what the paper says, I am not saying that. Okay. And the reason for that was, the primary goal of Multics in 1965 was security. It started as actually a computer utility and realized a need for protecting conflicting interest among the users. For example, user even they were trying to get more CPU time, right. So security started as a habit. When the baby was born, from day one it was tried to put into some secure habit there, right. So what happened later, when personal computers and workstations started coming up, people never thought they are going to be networked in such a massive manner. So people thought there was an incorrect conclusion that security is not important. I am only going to use, why should I bother, why should I buy all these things. But with growth of internet, security became very important, but all decisions made assuming less importance for security, those ill-founded decisions are haunting us today. You are getting the point? So there has been an era of development of complex systems with security put in the back burner. And those ill decisions, and now those same systems are now put into the internet and we are trying to retrofit security. The preventive approach to security based on authentication and secure communication is very weak, right. Today I say if you want to log in, you use the password, you use this, but there is something much beyond that we are feeling. Just by introducing one wrapper around it and say, if you want to come here, you should use this wrapper, it's not working out, because the wrapper itself is executing on a secure insecure platform where security was not a habit. And so this ignorance penetrates into that wrapper, right. So just by saying I will have good authentication and secure communication alone is not going to solve much of the problem. I could have all those things at the wrapper end, but the inherent weakness within the system can still expose your system to vulnerabilities, and that is the big takeaway from this paper. So the strength of Multics is there are something called buffer overflows. We will talk about what is buffer overflow in the next session, and what is buffer overflow, how it can lead to vulnerabilities. I will give it as one case study, right, which we will deal in the next session.